This lesson is on integrating using the natural log function. So in the previous lesson we derived functions involving natural log. Now that we know how to derive those functions, we're going to integrate functions that will antiderive into natural log functions. We're going to first start by looking at a couple of general power rules of integration. So if you want to integrate x to the 6 with respect to x, you'd add a power, divide by a power. X to the 7, divide by 7, so you get 1/7 x to the 7 plus c. If you want to integrate 1 over x cubed, you would write that as x to the negative 3, so you'd add a power, divide by the new power, you get negative 1/2 x to the negative 2 plus c. So whenever we're antideriving a power function, we're going to add a power, divide by the power, divide by the new power. So here I have the integral of 1 over x with respect to x. So this is x to the negative 1. Well, you add a power, so it's x to the 0, divide by the new power, so we get x to the 0 over 0. Well, there you have a problem because the denominator is 0. So we can't use the general power rule to antiderive x to the negative 1 or 1 over x. So now we're going to be able to antiderive using the natural log rules. If you remember in the last lesson, the derivative of natural log of x was 1 over x. So the antiderivative of 1 over x with respect to x is going to be the natural log of x plus c. But it's going to be the natural log of the absolute value of x. Remember, we want to take the absolute value of x because the natural log of something, you can't take the natural log of something that's 0 or a negative number. We talked about that a little bit in the last lesson, but just as a review or a reminder, natural log of x means e to what power gives you x. So if x was a negative number, e, which is 2.7 to some power, could never give you a negative number. So that's why we have to have these absolute value signs there. So we know this is always a positive number. The original equation here, since it's 1 over x, well, x can't be 0 here, so we don't have to worry about it over here when we antiderive. It couldn't have been 0 from the start, so it's not going to be 0 when we antiderive. The general antiderivative of 1 over u with respect to u, natural log of absolute value of u plus c, or the integral of u prime of u over u, u prime over u, equals natural log of absolute value of u plus c. Same thing, just two different notations. So if you have the derivative of something over the original thing that it's the derivative of, well, the antiderivative of that, the indefinite integral, will be natural log of the absolute value of that denominator. And we're going to see a few examples here. For this, just look at the above this line for the first one. Ignore this stuff below. That's going to be our second example. You have the integral of 6 over x with respect to x. So we're going to pull out that constant and make this 6 times the integral of 1 over x with respect to x. Well, the integral of 1 over x with respect to x is natural log of absolute value of x. So the integral of this whole thing is going to be 6 times the natural log of the absolute value of x plus c. One thing they might do, again using the rules of logarithms, 6 natural log of x, or absolute value of x, is the same as natural log of x to the 6th power. Okay. We can write it like that and eliminate the absolute value signs because anything to an even power squared to the 4th to the 6th will always be a positive number. So we don't have to worry about the absolute value sign if we raise it to the 6th power. It's important for you to be able to go between these two in case you're taking a multiple choice test and this is the answer they give you. You've got to be able to go from here to here knowing those rules of logarithms. Now we're going to do an example where you need to use a little u substitution, but it's still going to be the same idea. The natural logarithm function, the differentiation of it and the integration of it, allows us to antiderive a lot of rational functions where you have a numerator and a denominator because this opens up the 1 over x. If the denominator is to the 1st power, a lot of times it will be some form of the natural log integration. So we have the integral of 1 over 10x plus 5 with respect to x. Well, the first thing you want to do is use some u substitution. So u is going to equal the entire bottom in this case, 10x plus 5. du is 10 dx, so 1/10 du is dx. Now we can rewrite this. 1 over u and 1/10 du will go in. 1 over u is this part. dx is 1/10 du, so I get 1/10 times the integral of 1 over u with respect to u. 1/10 natural log absolute value of u plus c. Then you back substitute. 1/10 natural log absolute value of 10x plus 5 plus c. Technically, you could write this as a natural log of the 10th root of that also. More than likely, you won't see that. Now we're going to find area under a curve. Find the area of the region bounded by the x-axis, the line x equals 3, and the graph of y equals x over x squared plus 1. So you know you got x equals 3, a vertical line over here, this curve, and the x-axis. Well, this curve goes through 0, 0. When x is 0, y is 0 over 1, which is also 0. So we know this graph goes through 0, 0. So we were asked for the area under this curve between 0 and x equals 3. So we want to integrate using a definite integral to find area under a curve. Between 0 and 3, this function with respect to x. So again, you're going to use u substitution, where u, in this case, will equal the entire denominator. X squared plus 1, du is 2x dx. So you have x squared plus 1, you want x dx. So I divide both sides by 2, and you get 1/2 du equals x dx. 1/2, integral from 0 to 3, 1 over u du, equals 1/2 natural log x squared plus 1 from 3 to 0. Notice I didn't use absolute value signs here. It's going to be something you got to get a little used to when and when not to use absolute value signs. X squared will always be a positive number. Plus 1 will always make it more positive so that you don't need to worry about absolute value because you can't get a negative answer for x squared plus 1. So that's why they use parentheses here instead of the absolute value signs. Regardless, just like you did back in chapter 4, to find the area under the curve, you evaluate the definite integral, f of a minus f of b. I'm sorry, backwards. F of b minus f of a. Plug the top in, plug the bottom in, subtract the differences. So you get 1/2 natural log of 3 squared plus 1, natural log of 10. So natural log of 10 over 2, minus 1/2 natural log of 1. Well, the natural log, or any log of 1, is 0, because anything to the 0 is going to give you 1. So this part wipes out, so you're left with natural log of 10 over 2. If they ask you for a decimal approximation, you have to do that, 1.151, which looks pretty accurate here. This is well below 1 the whole way over, 3y, so 1.5 sounds about right. .15 sounds about right. Okay, now we're going to do an indefinite integral of a rational function where we need to use long division before we can integrate. So you have x squared plus x plus 1 over x squared plus 1. Well, you can see the top's not the derivative of the bottom. You can't factor anything and simplify here. So you're going to have to use long division to get this into a few terms. So you divide this out. X squared plus x plus 1 divided by x squared plus 1. X squared times 1 gives you x squared. So you get 1 times this is x squared plus 1. Subtract that, x squareds go, 1's go, you're left with an x. Okay? X squared doesn't go into x, so that's your remainder. So you get 1 plus x over x squared plus 1. So now you want to integrate 1 plus x over x squared plus 1 with respect to x. Well, integrate 1, you get x. Integrate x over x squared plus 1, you get 1/2 natural log of x squared plus 1. Again with the parentheses, plus c. We just integrated this in the last slide, so I'm not going to go through that whole process again. So again, if you see a problem like this where the top doesn't seem to be a derivative or a factor of the derivative of the bottom, then you might want to look into using long division first and that end term is where you'll probably have to use your natural log integration. Okay, here's something else. There's another different type of instructions. Same idea though. Solve the differential equation. dy dx equals 1 over x ln of x. When I want you to solve the differential equation, I want you to find the original equation. Y equals something. dy dx equals so, and I derive find y equals your original equation. This is a very, very common type of indefinite integral. They may put it in there as a differential equation. They may put it in there as an integral, a definite integral, an indefinite integral. Ask you just to find the antiderivative. But 1 over x ln of x is very common for them to try to trick you. The first thing you want to do is use u substitution. You can't let u equal the whole bottom, because if you do, the derivative of the bottom is going to be a product. It's going to be 2 pieces, and that's not going to help you. So we're just going to let u equal the natural log of x. So you're left with 1 over x when u equals natural log of x. The derivative of u is 1 over x dx, which is exactly what we have left. Since u is natural log of x, the derivative of this is 1 over x dx. So you can rewrite this integral as 1 over u du. Anti-derive, you get natural log of absolute value of u plus c. Back substitute, you get natural log of absolute value of natural log of x plus c. And you do need the absolute value signs here because you can have a natural log that's a negative number. Then you want to go back and said solve the differential equation. So you want to write it as y equals in the end. When it's asking you to solve a differential equation, it wants a y equals equation. So that covers integrating with natural log type of functions and integrals. Now we're going to use the natural log integration that we just did to find the antiderivatives, to find the indefinite integrals of the remaining trig functions. We can antiderive sine of x, we can antiderive cosine of x. But we haven't learned yet how to antiderive tan of x, cotan of x, secant of x, or cosecant of x. So we're going to use natural log integration to find the remaining 4 antiderivatives of the 6 basic trig functions. So the first one, we're going to integrate tan of x with respect to x. First thing we want to do is rewrite it. Sine of x over x. Sine of x over cosine of x with respect to x. Knowing that we're looking to do natural log integration, we're going to let u equal the denominator. So u equals cosine of x. du is negative sine of x dx. So, negative du equals sine of x. You can rewrite your integral. Negative 1 over u du. Integrate negative natural log absolute value of u plus c. Back substitute, negative natural log absolute value cosine of x plus c. Remember, cosine's a wave function, so it can be positive and negative, so we do need the absolute value signs there. One little equivalent form you might see. The negative out front could go to a cosine of x to the negative 1. 1 over cosine of x. So this is often written as the positive natural log of the absolute value of the secant of x plus c. Bringing this negative 1 as an exponent, 1 over cosine is secant. So instead of writing a negative absolute value or a negative natural log, they write a positive natural log and use the secant instead of the cosine. A very similar method would be used for the integral of cotangent. So if you have cosine over sine, so u would equal the sine, you'd go through. You'll see that in a few minutes. I'm not going to walk you through that one. It's very, very similar. You might even want to try that. You might want to pause this now, give that a try, and see if you get the same answer that you get in a couple slides. Sec and cosec are a little bit different, a little bit tricky to antiderive, to find the indefinite integral of. So we're going to go over how to do that. The idea here is that some mathematician, the one that came up with this, got a little creative. They took secant of x and multiplied it by 1. The form they chose of 1 was secant of x plus tan of x over secant of x plus tan of x. So when you multiply this through, you get the integral of secant squared of x plus sec tan of x over sec of x plus tan of x with respect to x. Now, you can use u substitution. Let u equal the denominator, sec of x plus tan of x. The derivative of sec of x is sec tan. Derivative of tan of x is sec squared. So du equals sec tan x plus sec squared x dx, which is the exact numerator. So, the integral of 1 over u du equals natural log absolute value plus c. So the antiderivative of secant of x is the natural log of secant of x plus tan of x plus c. The cosecant antiderivative was done very similar to this also. Here is a list of the 6 indefinite integrals of the 6 basic trig functions. Integral of sine, integral of cosine, integral of tan, cotan, sec, cosec. Just like the derivatives of the 6 basic trig functions, you need to memorize the antiderivatives of these 6 basic trig functions. So when you start doing your homework and doing these and seeing these problems, start trying to do them by memory. Start trying to remember them as best as you can. So, indefinite integration, actually just any integration with natural log functions is the same as it was before, now that you know that natural log integration rule. The integral of 1 over u du equals natural log of absolute value of u plus c. It's indefinite. So it allows us to integrate anything, not anything, but many functions that are rational and have a power of 1 in their denominator. So it opens us up to a whole new, a lot more functions that we can antiderive, find the indefinite integrals of, or find the area under the curve of that function between two x values.